just say now that a T-Liouville extension is obtained by adjoining elements y with either y prime is in K, so adjoining an integral, or such that y prime over y is in K. So adjoining what we call an exponential integral. And if K is in some sense closed under these types of things, so if the set of derivatives of K, the set of what's called logarithmic derivatives in K, so y prime over y, here y is a non-zero element of K, is equal to K. So for every element in K, I can find an exponential integral in an integral. Then K is called Liouville closed. Okay. So now the theorems that sort of describe in a bit more detail these various types of extensions.
Sorry, so T-Liouville and Liouville is the same?
Yeah, T-Liouville closed and Liouville closed are the same.
Yeah,
The difference is in the extensions, because Liouville extensions are just differential field extensions. T-Liouville extensions also have to be extensions as models of T. Yeah, exactly. Also, algebraic extensions are Liouville extensions, but models of T are already sort of real closed, so there's no need to consider this as well. Okay. All right, so the first one. This is going to be constant field extensions, given an extension. So now I'm considering C as a subfield of some C star, a model of my own minimal theory T, so an extension of models of T of my constant field. Then there is an HT field.
So when you do your real extension by adding forward the integral of the integral flow, do you do it such that the constants do not change, or it's allowed? Because sometimes if you do it, you already have a solution, you just add constant.
Yes, so I believe the Liouville extensions will allow for the constants to change, but the sort of, one can do this, and I'll say more in the Liouville closeness theorem, one can do this in such a way that the constants don't have to change. Yeah. So of course, Liouville closed does not mean closed under all Liouville extensions, because one could obtain more just by adding new constants. But yeah, one doesn't have to arrange Liouville closeness. Right. So given an extension of my constant field, just as a model of T, there's an HT field. With these new constants, with the universal property. So if I consider C, my constant field, and this larger constant field, and then I can amalgamate these into a new HT field. And then the property is, of course, that if I have some other HT field L, K embeds into L, these new constants embed into the constant field of L, this agrees on C, then there's going to be a unique extension here, which makes everything commute. So in the same paper, I deal with these Liouville extensions. If K is omega free, maybe I'll say more. This is just for now some technical assumption that needs to be made. Then K has a Liouville closed. extension k star with the semi-universal property that we would expect. So if we have k and k embeds into another U of O closed field L, then there is an embedding of k star into L, but not necessarily a unique embedding. Omega freeness is needed for this to be true. Really something slightly weaker called lambda freeness is needed. I won't really say much about what these are, but I'll just say without them, there's this sort of fork in the road which occurs, in which k can actually have two Liouville closures which are not isomorphic. Essentially, this sort of comes about if you have something that you need to integrate and you need to decide whether it has an infinite integral or an infinitesimal integral. Omega freeness means that you never have to make this choice, essentially. So as far as the TD transcendental immediate extensions are concerned, if K has no proper TD algebraic immediate extensions, so if I don't have to worry about anything in this sort of mystery box that I erased, then any immediate extension where I join a new element is determined by the cut of A. So this immediate extension is completely determined by the cut that A realizes over K. Something that I'm writing up now is that if K is Liouville closed, and has no proper TD algebraic immediate extensions, then K has no proper TD algebraic extensions at all, as long as I don't grow the constants, because I can always grow the field of constants, so with the same constants. So this really tells me that the chart that I drew up here is completely exhaustive. This thing down here about the infinite rank value group extensions, this is sort of the key ingredient needed to prove this theorem. Basically, it says that the only way that you can grow your field under these assumptions is sort of growing in an infinitary way, which would rule out being a TD algebraic extension.
So here you are with the same constant, because you could always add constants?
Yes, I can always add constants, and that will be a TD algebraic extension, exactly. And then finally, as far as the TD algebraic extensions are concerned, the immediate ones, we can show that K has an immediate HT field extension L that is spherically complete. which is to say that any nested family of closed evaluation balls has non-empty intersection. Which is to say that these TD algebraic immediate extensions, we know in some sense that we can adjoin them. What we don't really know about is whether there's some sort of semi-universal property that comes from adjoining them, whether they can sort of be adjoinable in a relatively canonical or relatively unique way. Okay, let me just give an application. Of this second theorem here. So R and X, because this is the expansion of R by restricted analytic. Functions with the unrestricted exponential. So we're sort of leaving the world of polynomially bounded minimal structures for this application. We can extend these functions to t. Well, the transseries has on it a natural exponential. As I said, it's a logarithmic exponential field. As for the restricted analytic functions, we can make sense of these on T using Taylor series. So we can just plug one of the power series into T, or several of the power series in T, into the Taylor series for this restricted analytic function, and we'll get another thing in T. So this expansion, denoted by T and X, this is an HT field. For, of course, T is the field of this thing. Okay, and so now, if H is an R and X party field, we have the following. So H has a Liouville closure, which I'll denote by Li and X H. So what is this? This is an R and X party field, which is obtained from H by adjoining integrals and exponentials. As a Hardy field, this Liouville closure business is due to Busch-Nitzen. I guess in the case of our Hardy fields, this is due to McIntyre, Marker, and Van Dries. If I have an embedding of this Hardy field H into T and X.
Would you like the first before X? L.
So this is Li for Liouville closure,
Yeah.
and for restricted analytic functions, an,
Okay.
and then x. So this is going to be, one could think about this as sort of the minimal Liouville closed Rnx party field extending H. And so if I have an embedding of H into the transseries, then this will extend to an embedding of this Liouville closure. And all of these embeddings, by the way, are embeddings which respect these additional functions. So they respect the restricted analytic functions, they respect the exponential, and of course they respect the derivation. Of course, to get this, one can't apply this exactly. First of all, this isn't a polynomially bounded thing, so one has to deal with adjoining these exponentials as well. Secondly, this omega freeness might not necessarily be true for H, but one can sort of show that this fork in the road phenomenon that I talked about doesn't occur in the specific setting.
Yes. So, for example, here, if H is in Hardy field, does it mean that you can associate, in some sense, to the germs of the extension a kind of transasymptotic expansion? Is it what you mean?
Yes, so that's a good question. So if H embeds into, this shows that any embedding like this extends to an embedding like this, although this doesn't really say anything like if this is some sort of truncation closed embedding, can this be taken to be truncation closed?
Yeah.
Not sure, no. Yeah.
So here next is you will take the trans-series that you talked about before, and then the next means just that the other of those operations defined on them.
Right. So this is the same underlying differential field of trans-series, but now I'm also considering it in this larger language where I include a function symbol for the exponential and function symbols for all of these restricted analytic functions.
Okay, and if H is an R and X part of the field, so the embedding of H in T and X is unique, exists, or I forgot what you said.
Oh yeah, so I'm saying any embedding of H into here, which may not exist for arbitrary Rnx party fields, but if there's such an embedding of H, then there exists an extension to the Liouville closure.
So the embedding is like asymptotic expansions of the functions.
Exactly, yeah. The embedding should be thought of as sort of formal asymptotic expansions of the functions in H.
Okay, but there is no theorem saying that this exists, or
no, but there are lots of examples in which we know that this exists. But yeah, there's no theorem in general which says if this exists, and in fact there are known to be Hardy fields for which this does not exist.
and if it exists, it is unique or not?
Not necessarily, no. Right. And as I was saying to Jean-Philippe, even if we know this embedding here is maybe truncation closed or something like this, that it also respects something about the power series nature of the trans-series, we don't necessarily get this for the embedding of the Liouville closure.
You mean that you have counterexamples? Is it what you...
I don't have counterexamples. I mean, I think that in practice, it seems plausible that one could arrange such an embedding, but one would really have to get in there and do it, as opposed to relying on some model theory, extension results.
Okay.
Yeah. Okay. So in the last, I guess 20 minutes, I want to maybe talk about these immediate extensions. This is the box with the question marks. So what do we still need to do? One. First order characterization of 1K has no proper TB algebraic need extensions. And 2, show that K has a unique subisomorphism. TD algebraic immediate extension with this property. This property of having no further proper TD algebraic immediate extensions. So for those who know something about value fields, this is to say that we need analogs of Henselianity and Henselization. So at least in the echo characteristic 0 setting, Hensellianity tells us when we have no proper algebraic immediate extensions. And the Henselization is sort of an algebraic immediate extension with this property of being Hensellian. Okay, so as far as generalizing Hensellianity to the differential setting, there is, of course, something known. This is differential Hensellianity. This is the natural thing to consider.
But I think in the theory of value field, because what is called a defect thing,
Yeah, so
you could have things which are Henselian with a lot of defects, so there are immediate extensions.
But not
No. As I said, this is an analog.
Okay.
This is an analog with valued fields of residue characteristics zero.
Okay.
Yeah. And all of the fields I'll consider here, of course, will be characteristics zero. So this doesn't come up. So this is the natural thing to consider. Of course, there are two problems with considering differential Hensellianity. The first is that this is just a differential algebraic thing. It doesn't take these minimal functions into account. And the second thing is that the axioms of differential Hensellianity tell you when you can lift solutions to differential equations from the residue field to your field. But of course, the derivation on the residue field is trivial. Right, the residue field is just isomorphic to the constant field. So we're not going to gain anything from lifting solutions to differential equations over the residue field. So what works for H fields is what's called Newtonianity. And this is an eventual version of differential Hensellianity. So let me try to draw a picture. So the first thing to note is that anytime we have an H field, this is going to be a differentially valued field in the sense of Rosenlicht. What this means is that the derivative and the logarithmic derivative induce well-defined maps on the value group. So this here will be the value group. Of my field. This is the map which takes gamma to gamma dagger. This map takes gamma to gamma prime. What I mean by this is that this map is defined by taking something in my field with valuation gamma, taking its derivative, and then looking at its valuation. And this doesn't depend on the choice of representative. This is given by taking something in my field with valuation gamma, looking at, let's call this thing f, looking at f prime over f, the logarithmic derivative of f, and then looking at its valuation. Once again, this doesn't depend on the choice of representative, except if I choose things with valuation 0, which is why I drew this little circle here. This is not defined at 0.
So gamma plus is simply gamma prime minus the identity or not?
Yeah, exactly. So gamma plus gamma dagger. Okay. And now what I'm going to do, okay, as I said, the derivation on the residue field is trivial. I want to consider some sort of field with non-trivial derivation on the residue field. And the way I'll go about this is by coarsening. So I'm going to coarsen by delta, which is going to be the set of all gammas, such that gamma dagger is bigger than 0. So if I draw this here, I'm going to coarsen by this, this convex subgroup, this box, and I'll end up with something. The residue field will correspond to the things with valuation inside of this box. So the derivation on the residue field will be non-trivial, and I can work with this. In the case of Newtonianity in H fields, basically Newtonianity says that when I coarsen, I get something differentially insilient.
What is the word you said?
Coarsen. So when I consider the valuation to gamma mod delta, the corresponding residue field will consist of things whose valuation lies in delta. And then this will have non-trivial derivation. So I'm going to ask that this coarsening, this thing with a larger residue field, be differentially insilient. And this will actually mean something because my residue field, when I have non-trivial derivation, it makes sense to ask for me to lift solutions to differential equations from the residue field to the big.
But delta is not a group because of 0.
This is all the gamma with gamma dagger bigger than 0.
But you said that for 0 it's not defined.
Yes, okay, along with 0. Okay, and so this is just one particular coarsening, which of course, gives me something, but maybe doesn't tell me so much about my field since I'm sort of shoving a lot of my problems into the residue field. What they do is they do this coarsening process while also doing this thing called compositional conjugation, which is when they replace the derivative on their field with phi inverse times the derivative. For phi having valuation somewhere below this thing. So what this corresponds to in this picture, when I replace the derivative by this thing, is you push these two pictures, you push these two graphs downwards. So you're pushing this downwards while still asking that it sort of peak above the positive axis. This will amount to shrinking this box smaller and smaller. So I'm getting finer and finer coarsenings.
What is phi?
Phi is going to be, so let's see. V phi will lie somewhere here. So it'll lie somewhere under this thing so that when I subtract off phi, I'm moving this graph downwards, but it's still going to peak above the positive, above the x-axis here.
Well, you take 85 such that
Yeah, so I'm going to take phi to be larger and larger.
Yeah.
So I'm pushing this more and more down. And since this square is determined by the intersection with this axis, the square will get smaller and smaller and smaller. So I'm considering finer and finer and finer coarsenings, and I will ask that these all be differentially insilient. This is the definition of Newtonianity. Okay.
So the graph gamma prime goes exactly through the corner of the square or not? The square is said that this graph goes exactly.
Yeah, I think that's probably right. Okay. So I have not worked on developing a notion of Newtonianity yet in this setting. What I've worked on because of this sort of process is developing a notion of differential insilionity that makes sense in this minimal setting. So we developed a notion of TD insilionity in joint work with Nigel Pincoats. I don't think I have time to say exactly what this is, but it's something similar to differential Henselianity. It says something about, I guess you can view it as sort of lifting solutions to a minimal differential equations from the residue field to the larger field. It's not exactly like this, but that's sort of the flavor. The isolated property that ensures the neatness of spherically complete immediate extensions. This is called the TD Hensel configuration property. Essentially what it says is that definable functions are in some sense well approximated along pseudo-Cauchy sequences by linear differential operators. And this is what's needed to get things working. Once we have this working, we use this to axiomatize the existentially closed structures So we axiomatize a class of existentially closed structures for a sort of easier theory than the theory of HD fields. These are going to be structures M, O, D, where here I'm going to require again that M is a model of T. Next, this valuation ring O, I'm going to ask that it is something called T convex. This is a sort of compatibility condition for valuation rings on minimal structures isolated by Van den Dries and Muhlenberg. This is closed under zero definable continuous functions. This was not something that I asked for HT fields, by the way. It actually follows from the axioms there. But here I'm going to have to insist on it. And thirdly, I'm going to ask that the derivation is a monotone. T derivation, which means that the derivative of everything, the derivative of anything is bounded by that thing, which is to say that the logarithmic derivative, a prime divided by a, lies in my valuation ring for all non-zero. So for these class of structures, we isolate a model companion. The model companion will have among its axioms this TD Henselianity. Since I'm not requiring here that the valuation ring is equal to the constant field plus its maximal ideal, this allows for larger residue fields. And in fact, in the model companion, the residue field will be quite rich. It will come equipped with a derivation which will behave in some sense generically.
What is M star? M different from zero?
M different from zero, yes. And of course, we still need to get this working in a broader setting. So this last condition of being monotone, this is a sort of, maybe somewhat natural thing to ask, and it makes everything work out well. But for example, there are lots of Hardy fields, lots of H fields in which the derivative is not monotone. For example, as soon as you have an exponential around, it's quite easy to cook up examples where this doesn't happen. So we need to get this working in some broader settings. And let me just end by saying a couple of cases where we know that differential equations of this form have Hardy field solutions if and only if they have transfer solutions. So the first one is restricted elementary ODEs. So that is to say when f is definable in the real field extended by the exponential function, but restricted to the interval 0, 1, and the sine function restricted to, let's say, the interval 0, pi. So I did this in the last part of my thesis. This isn't too much of an extension of the theorem of Aschenbrenner, Dries, and Hoeven. Essentially, this just requires you to observe that the restriction of these two functions to the maximal ideal are already definable. Exactly. And then use some formulas and a couple of other things to get through. A little bit more difficult is when f is a signomial function. So that is to say when f is definable in the reals with x maps to x to the r. And this follows from a recent preprint. And the sort of nice feature of the setup that I give here is that it allows you to also quantify over these real exponentials. Although, of course, doing it for this structure, I think, would not be so much more difficult than the Aschenbrenner, Dries, Hoeven theorem. Allowing for quantification over the real powers takes a little bit more work. And I'll say that this is still open. And seemingly rather difficult for f definable in the reals with the unrestricted exponential function. And I think that handling this extension, one does not need to use the sort of minimal machinery that should be something, sort of differential algebraic, but it still seems to be quite difficult to do and maybe sort of complementary to the polynomially bounded setting that I'm usually dealing with. Great, so thank you.